Good afternoon or good morning, depending on the time you are listening to this seminar. This is the 6th seminar in this Prime series, and I would like to thank Arish, who's the head of the radio system research at Nokia Bell Labs in the United States, for accepting our invitation for this webinar. And also I'd like to thank Pedro Santos, who's head of the network deployment at Vodafone Portugal, who's a partner of FEUP, and we've been collaborating in education and research activities. I'd also like to thank Ana Aguiar, who made the introductions to both Arish and Pedro. And I'd like to thank the people who are being supportive of this event, in particular Marta and my colleague Anna, another Anna, different from Ana Aguiar. And I'd like to thank also the people in charge of the technical support, Miguel Marques, for helping us with this webinar. This is the first webinar on the technology of telecommunications, on the future of the communication standard, and I'm looking forward for listening to the presentation and to the questions, and I hope all the audience that is listening to us will benefit from this webinar. So please, Arish, thank you for being here, not being here physically, but being here with us. So please, you are welcome to start your presentation.
Thank you, Joe. So let me start by sharing my screen here. Okay, this is, Are you seeing the right presentation? Does it say communications in the 6G era?
Yes. Mm-hmm.
Okay, good. Okay, so thank you very much for inviting me to this seminar series. I'm very pleased to be here online and happy to make this presentation. So as you all know, cellular systems have been evolving over the last 30 years. A new generation of mobile networks is introduced every 10 years or so. And I'm going to focus my presentation on that aspect of telecommunications, mobile networks, knowing very well, of course, that there are other aspects like fixed line optical networks, backhaul networks, as well as Wi-Fi and things like that. But my focus here is on the cellular networks. Okay, so I would like to start with a historical perspective. So what you see here is the evolution since the 1990s. We introduced 2G with 200 kilohertz signal bandwidth, primarily targeting mobile voice communications, and messaging was another application that was added to that, but the main focus was voice. If you look at the evolution from 2G to 3G, we went to wider bandwidths, 5 megahertz, so we could accommodate new use cases, which in the 3G timeframe meant really being able to download websites, broadband data for the first time mobile. At the same time, the key focus of 3G was about low-cost voice, how to optimize voice, increase voice capacity. As mobile phones were becoming much more popular, there's a big demand for voice capacity. And so that was the main focus of 3G. If you look at 4G, it's the next iteration of these cellular systems. So we went for even wider bandwidths, which now allow really true video streaming. And then we also introduced the new use case of Internet of Things in the LTE, M, and narrowband IoT systems. But at the same time, 4G was all about reducing the cost of data capacity. And by the time of 4G, voice was essentially free, meaning it was added to all the data plans for free. And the trend continues. I think what you observe from this is that each new generation is about increasing the data rates, going to higher data rates to support new use cases, and also introducing something really new in terms of what it supports. So in 5G, the industrial IoT with the ultra reliable and low latency is the critical new service. And also the support for, say, virtual reality, augmented reality. But at the same time, it's about reducing the cost per bit and reducing the cost of the previous generation use cases. So the main message I want to convey is each new generation of mobile networks is about reducing the cost and increasing the efficiency of the new use cases of the previous generation, but at the same time introducing new use cases for the current period, for the current generation. So what is 6G going to introduce new is the big question. So we like to think in terms of augmented human. So when we talk about 6G, we are talking about mobile networks from the 2030s to 2040. Every generation lasts about 10 years. So what do we mean by augmented human? So the first is augmenting our experience. We will move from creating and consuming multimedia to really producing and consuming entire digital worlds. These digital worlds might be the twin worlds of the physical world or pure virtual worlds. But all of the new applications will now be built on top of the digital world experience, just like today's applications are largely built on top of multimedia, video, voice, and data. So some examples of use cases I've provided there, which we will talk about a little bit more. So it could be like multimodal, multisensory telepresence, which is very apt for a period like this. It could also be about mapping the physical world in real time, dynamic digital twin creation. It could be in factories where remote collaborators can work together to create new designs using both physical and virtual objects. The second one is about augmenting our intelligence. So with the introduction of pervasive artificial intelligence and machine learning, humans will have the opportunity to expand their knowledge and intelligence. So we are going to be able to learn and learn from and with machines. So what does that mean? So like we are searching for information today, we may actually rely on machines for intelligence. So one early example of that could be the digital assistants that are already showing up, like Alexa, for example. It's not just about information anymore. You're relying on the machine for keeping track of many things, making logical decisions and things like that. Another example of a use case would be automatic security. If we enable our infrastructure sufficiently to gather and process data, then it can solve problems related to security. You may not need to stand in security lines in front of, when you enter the airport or other areas. It can be all automated. Then the third one that augments our intelligence, as an example, is about our own body, the physiological parameters. We sort of know them through our own sensing mechanisms, but there's a possibility to augment that, gather even more intelligence about that. So, and that can have applications in healthcare, obviously. And the third one is about augmenting our control. So this is really about being able to control the new machines that will appear in that 2030s, domestic robots beyond the vacuum cleaner robot that we may be using. It could be about remote driving, self-driving in dense urban, probably not likely to happen in the 2030s. Will take longer. So remote driving could be something we could enable. And then there could be multiple robots that are collaborating with each other, drone and robot swarms, etc. So with all this, I think what we are saying is that in the 2030s, the goal of the infrastructure would be about augmenting human potential and well-being at scale, way beyond what we can do. So introduce essentially something fundamentally new in our experience. So whatever I said so far, you can sort of summarize by saying that it's about the interconnection of the physical world, the digital world, and the biological world. The biological world being the world of physiological parameters of humans. And we are really talking about high resolution, almost real experiences that are created in the digital worlds. So 5G will introduce augmented reality, virtual reality, and we will take that to the next level by creating entire digital worlds with the multi-sensory experience like touch, and some people even say maybe a sense of smell and things like that. In order to accomplish that, we need not just the 6G connectivity, but a set of surrounding technologies that will enable that. One being the precision sensing and actuation. So in order to map the physical world, we need better sensing, and also to control these machines, we need better actuation devices. Computing is going to become much more ubiquitous and much more integrated with the communications, because we would have to rely on computing that's available not just on a particular device, but on an adjacent device or in the edge cloud or some other device that's available through a LAN or something like that. So integration is critical, and especially because we want to also not be restricted to large devices because we need the compute. So we want to go smaller devices and rely on external compute for those devices. Then we have knowledge systems, which are basically AI software that is about processing all the data, creating models for prediction. So if you think about what knowledge really is, it's about being able to assimilate information and predict what the future is going to be, or even understand the intent of humans. So it's for even for network management, as an example, we want to be able to do intent-based management. So systems that can take human intent and turn them into actions for the network. And the last one is to truly experience digital worlds, we need much better human-machine interfaces. The smartphone will likely become disaggregated into multiple devices, display devices, and wearable devices, textile devices, and whatnot. So overall, all of these technologies together will enable the unification of our experience, the augmented human experience across the physical, digital, and biological worlds. And this is the goal, I think, for the telecommunications infrastructure together with the surrounding technologies. So a little bit about the use cases before I dive into the technologies. So the first one, as I mentioned, is the multimodal mixed reality telepresence. It could be an indoor as well as an outdoor use case. So you could be driving in a car and then you want to join a conference, and to the people in the conference room, you appear like you're in the office. So you want to be anywhere, anytime, and any way you want. And this is possible by combining physical and virtual worlds together to create the experience. So multiple streams of data, each at high resolution, being combined together to create this experience. Spatial computing is about positioning the objects in this digital world at the right places. So you have your own images, you have images of other objects, and you want to position them, like a clock, for example, is coming from one place, you are coming from another place, but everything has to be synchronized and appear to be coherent and in the right places. So there will be a need for a lot of spatial computing to enable such use cases. And then synchronization across the different streams of data becomes critical. If you think about what it takes to do something like that, this document that's already there in IETF helps us understand that. Obviously, the goal is not to go through everything, but they break this up into entry-level VR, advanced VR, and ultimate VR as an example. And what is different is the resolution in terms and the frame rate, things like that. And you can see that to enable an ultimate VR experience, you need very high mean and peak bit rates. And of course, this is without advanced compression strategies that we will invent in the next 10 years or so. So you could, for example, do things like foveated streaming, which means that you only send in high resolution what the human is seeing, and the rest is not sent in high resolution, and you turn your head and the rest comes in higher resolution. We need low latency, we need very high level of synchronization, etc. And you need also localization at the centimeter level to be able to place the objects in this spatial computing that I talked about. But with all the compression, it does seem like you can do these sorts of ultimate VR experiences in real time because it takes about a gigabit per second, let's say, at scale, meaning multiple people are able to participate in these sessions from our telecom infrastructure. Another example is this high resolution mapping. Here we are talking about mapping of the physical world. So you can see that all these cars will be gathering a lot of data, both through the cameras as well as through other radars, etc. And if you collect all the data from every car, semi-autonomous car that's out there, you can actually create in real time where the pedestrians are, what is happening on a street and at an intersection and things like that. And you would need enormous amounts of uplink bandwidth. So if for example, to send all the information gets gathered from all the cars, each car is going to generate sensor data of the order of hundreds of megabits per second. And with all this, of course, you need machines on the other end to process them. You can start predicting with high accuracy movement of people, movement of cars, and make the whole city much more efficient using applications that are on top of these digital twins. So what this is about is really creating a digital twin of the city in real time, and then building applications on top of that using real-time analytics and other advanced technologies. So this again requires enormous amounts of outdoor uplink bandwidths that we need new infrastructure for. Sensing is another area. So we talked about augmented intelligence. So here it's about enabling the network to do the sensing. Of course, we can do sensing using separate devices. We carry around our smartphone that has a lot of sensors, and we can put tags on various objects. But what we're talking about here is to enable every base station, every access point to become a radar device as well. So just like the communication revolution that we created, we want to create a sensing revolution by enabling that. And the reason why it makes sense to do it at this time is because we are going to higher frequencies, wider bandwidths, so we get better resolution in space and in time. We have narrower beams. All of this is needed for communications. Then why not reuse that also for sensing? So this is likely to become an essential component of our future systems. And the variety of applications could be over both indoor and outdoor, things like traffic monitoring, drone detection, etc. And in the indoor, it could be about detecting presence of people where they should not be there, or understanding what the warehouse situation is like, etc. Of course, you can do these things with cameras too, but radio sensing will augment the cameras in certain ways, where cameras cannot be used, or around the corners, behind walls. These kinds of things can be enabled by the radio. Okay, in terms of thinking about building the telecom systems, if you think about how we've thought about building systems, it's about capacity, reliability, and latency up to 5G. And there are only three fundamental resources that we have exploited: spectrum, spectral efficiency, and spatial reuse, right? So these are the three resources. We get more spectrum for higher data rates, wider bandwidth systems, or even for reliability. We use multiple bands to make it more reliable, or we reduce latency by going to shorter symbols because we have now wider bandwidth signaling. Similarly, spatial reuse, put more base stations to increase capacity, or create multiple paths for reliability to reach the same device. All of these techniques are there and rely on these three dimensions. But in the future, I think that three more dimensions are going to become really important. One is data, because there will be pervasive use of AI in the networks for network optimization, even designing certain aspects of the network. And so the more data we have, the better our trained systems will be. So data will essentially become like a fundamental resource to exploit. How we gather and analyze and exploit the data for training our AI systems is going to become as important as spectrum in the future, is what we can say. Energy is going to become very, very much a focus of our 6G systems, telecom systems, as we go towards this, carbon neutral systems. We need to pay much more attention to energy and treat energy as an important resource, not as something that's easily available. And finally, as I said, compute. also becomes a resource to exploit, because Moore's law itself may saturate, and we have to rely on compute that's available in multiple different locations. So we have to think about how to integrate the communication and compute and make use of compute wherever it's available. So finally, in terms of the technologies, I talked about most of these already. So AI ML will be pervasive, and we are thinking that even the basic design of the air interface could be exploiting a lot of the machine learning techniques. It can allow for fast adaptation of the air interface depending on the scenario. And the way we do research and development will also be transformed if this really takes off. New spectrum technologies here refers to going to even higher spectrum bands like sub-terahertz for backhaul or for very short-range communications, as well as the next generation of massive MIMO. We talked about the network as a sensor. There will also be architecture enhancements, like we want the network automation and simplification by combining some of the functions today that are like duplicated throughout the network. And as the RAN functions move towards the cloud and the core of the cloud moves closer to the edge for lower latency, it makes sense to combine and remove duplication. At the same time, the microservices-based implementation gives us more capability to specialize the network for different purposes. Extreme connectivity. This is about the the high reliability, low latency, and global coverage that we need to provide. So extreme forms of connectivity in various dimensions. Finally, in the 6G era, we will need much better security and privacy, because there are new forms of communication. Like when you create all these digital twin worlds, privacy takes on a completely different dimension, in the sense that you have to now watch the video streams, audio streams, and remove private information, not just from text and web pages, browsing, and things like that we are doing now. So all of these will, I believe, be the essential technologies for 6G. So to answer our question that we posed before, our prediction is that 6G will further continue along the trend, end up with wider bandwidth systems through new spectrum that's available. And the new use cases that 6G may introduce are based on the sensing and the creation of true high-resolution dynamic digital twins. At the same time, it will optimize the use cases that are first introduced in 5G, like the industrial IoT, make them more low cost and make them better performing. And of course, I predict that we will have pretty much zero marginal cost for data, voice, IoT, and all that, because the cost per bit will be so low. Okay, thank you very much. That's pretty much what I wanted to say.
Thank you very much, Harish. Right on time. And thank you for your presentation, interesting presentation. And now I will introduce the other guest, Pedro Santos, who's head of the network deployment at Vodafone Portugal, and who's going to ask some questions and discuss the presentation to start with. So thank you. And welcome, Pedro, again.
João, thank you very much for the invitation. It's a big pleasure being here, and thank you, Harish, for the very interesting presentation. Especially coming back to my university is always a pleasure, even if in a virtual mode. It's good to be here and to share, of course, my thoughts and my questions with you. So a bit of my some information from my side. So I'm responsible, as you said, for the network deployment at Vodafone Portugal. Within that, I have the pleasure to lead also the 5G program within Vodafone. And this is, of course, something that we, despite not having a commercial launch of 5G network yet, this could lead to a long story discussion. But we are working with this 5G for 3 years now. 3 to 4 years now, so it's something that we already have a feeling on the goods and the challenges. And as I understood from Arish's presentation, some of the evolutions and fixes, let's say, that we are seeing the limitations in 5G might come in 6G, which is good. And this leads to some of my questions that I will send it over to you, Harish, that could trigger the conversation. The first one is to deliver all the, let's say, the advantages and the characteristics of the 6G. Of course, we are talking about going and moving to even higher frequencies. So my first question is, what kind of frequencies, so spectrum-wise, are we thinking of when talking about 6G, and what is being thought to cope with the limitations that these high frequencies brings us in terms of coverage? Because we are already seeing this into the 5G when we are talking on frequencies only on the 3.5 gigahertz, but moving to millimeter wave, we face lots of limitations.
Right, very good question. So in 5G, as you know, we have three bands, right? One is the sub 2 gigahertz low bands. Then we have the mid bands, which is like the 3.5 gigahertz. And then we have the high bands, which is the millimeter wave. So we believe that 6G will be similar. So in the sense that there will be the new mid bands from the 7 to 15 gigahertz or so, which may be the main band for 6G. So there is still a lot of work to be done to make that spectrum allocated for 6G, but this is work that we will do over the next 10 years through various forums, ITU, World Radio Conferences, and the various government communication commissions, etc. So that's one band, and there I think we will probably see the most traditional mobile networks, just like we are seeing today in the 3.5 gigahertz. Then we will have the sub-terahertz bands. I think the role of that will largely be for backhaul, but now the backhaul will be integrated into the access. And of course, it'll play a role in the indoor communications. So a lot of the very high data rate applications tend to be indoor. And so we are thinking that we can use the sub-terahertz, like in a mall or in an auditorium. In these types of contexts, we could exploit the large amounts of spectrum that's available for access. And outdoor, maybe we'll use it for really short range in dense urban, like millimeter wave today, but really for backhaul outdoors. And the backhaul will be integrated into the access. And then finally, we also expect that there will be the low bands of 6G. This is probably coming to us some spectrum through the re-banding of the digital TV spectrum. Still, some spectrum is available in those bands. So that's how we see it. And of course, we cannot beat the limitations of physics. So these higher bands will necessarily be only very small cells. So in the millimeter wave, we talk about 100-meter cell sizes, and we are seeing that in the sub-terahertz, we could probably get to, with a technology that's we think will be available, maybe 30 meters, something like that. So still less, and so the applications will be more limited for access.
Okay. From an operator perspective, and this interests me particularly, of course, in terms of deployment. So as we see it today, we have a combination of, let's say, macro cells deployment together with smaller cells deployment and indoor systems. Let's say the industry promised, probably since back from the 4G, that the number of small cells would be increasing a lot, but what we can see is that never ramped up quite spectacularly. So do you foresee that in 6G we will be seeing more and more this proliferation of small cells integrated in furniture, urban furnitures, or different structures than we are not used to see today in the normal deployments?
Yeah, I will tell you why I think that the small cells did not happen as was predicted. I think the biggest reason is massive MIMO. So if you think about it, people were right on predicting the need for higher capacity. And then for that reason, they predicted that we will go to smaller cells if we really want to meet the higher capacity demand. Mm-hmm. But then came the massive MIMO technology, which allowed us to scale the capacity without having to go to smaller cells. So we practically, increase the capacity from like LTE with 4 antennas to 5G with hundreds of antennas, 200 antennas and 64 TRX. We could increase the capacity by a factor of 4 to 6. And so we could also, the coverage in these higher frequencies became comparable, higher meaning the 3.5 gigahertz became comparable to, say, the 2 gigahertz because of these large arrays. So we could manage to provide the capacity with the traditional deployment models. But if you think further ahead, I don't think we have something in our pockets that increase the spectral efficiency of macro cells to that extent. So we've already exploited the massive MIMO. Now we could go to even larger arrays, which I think we will do. That may give us some improvement in the capacity, but I feel like we are at the point where that, everything that we can do to increase the spectral efficiency of macros has been done. And so as far as I can tell, the next big frontier has to be the densification. And I think it will start already in 5G with millimeter wave. So once all the 3.5 gigahertz deployments are completed, operators will start focusing more on the millimeter wave. Maybe it'll start with indoor first, especially in the verticals like ports, harbors. I think those places where they need high capacity, of course. And then we can see the dense urban and fixed wireless access and things like that. So I feel 5G will already create the foundation of small cells before we go into 6G. That's my feeling.
Okay. Thank you. You've mentioned massive MIMO, and it's absolutely true. So it's a very clever way to compensate for the physics and bring the extra capacity, as you've mentioned. But this brings another problem into the equation that we are facing already in 5G, which is the power consumption that these new units are bringing to the networks. And as you've mentioned in your presentation, so let's say the environment is a reality, right? We need to, and this is a strong driver, not only from the cost perspective on the operator side, but also on the planet. How do you see that the suppliers are evolving to bring this consumption down and the level of complexity of the technology going up? So this is a very difficult equation, right?
Yeah. So I think there are two things that help us reduce the energy consumption. One is getting closer to the user, which is the small cells, right? The more you have wired communication and less wireless, so to speak, the more energy efficient you are. So going to smaller cells is going to increase the energy efficiency overall of the wireless systems. And more of that we see, the more energy efficient we become. The second thing I would say is learning to adapt to users. So one of the biggest problems we have in the cellular networks today is the energy consumption is not proportional to the use of the network, right? So there is so much energy consumption even to support one user or two users sending at low data rates. Because the system is designed for many users communicating at high rates, but it doesn't lower the energy consumption if you go to lower. So for example, as in the example of massive MIMO, we build systems with so many transmit receive chains that are all consuming energy. So we are investigating new ideas like turning off arrays and making it a smaller system when there's less traffic, And then we can also go to the extreme of turning off some cells if you have a lot of small cells with overlapping footprint. Then you could potentially, like if you have macro and small cells, we could turn off some small cells, etc. So these are all some technologies that I think will become more mature to make us more energy efficient. There's a lot of work already in 5G to make 5G systems energy efficient, and I think that trend will continue. And I know that Nokia, for example, is making a commitment to become, I think, almost carbon neutral by some date, 2040 or something like that. Don't quote me on that. I don't know the exact date, but something like that. So I think all the vendors are committed to making the systems much more energy efficient.
Okay. Thank you. This is clearly a very important pillar also for us that then are deploying these networks on the field. Moving maybe more to the use cases field. You've mentioned in your presentation that some improvements on the uplink, especially to meet the requirements of the sophisticated use cases would be needed. And that's exactly what I feel when looking into 5G today. It brings a very big step forward in terms of the downlink performance today, together with the low latency and all the other ingredients, let's say. But on the uplink, I feel it's still short. So the network is still very unbalanced. So it's very strong on the downlink and weaker on the uplink. So the uplink is clearly the weakest path. Do you think that this network architecture that has to be closer to the end customer is what will crack down this problem, or anything else that you think it's interesting on the uplink that will make 6G?
Yeah, I think you're perfectly right that that's the ultimate answer, to bring the base station closer to the user, because we are limited by the power on the devices on the uplink. So we are not able to use the wide bandwidth that we can use on the downlink on the uplink. Each user gets to use a narrower band because they don't have the power to use the whole, and hence the data rates on the uplink go down. And also, some enhancements through massive MIMO will help. I mean, if the devices themselves start having more antennas, then we could potentially do more streams, more layers between the users and the base stations, and that can also increase the uplink. So if you think about massive MIMO, most of the discussion is on the downlink when it comes to increasing the capacity so far. And the reason is that we're not still working hard on uplink MIMO, so to speak, for a single user uplink MIMO. So enabling more layers from each user, again, that requires power. That's the reason. So as the cells get closer, we will not only be able to use wider bandwidths, but we can also implement more layers for each user. More layers meaning more streams of data that can be resolved at the base stations, right? And so you can increase the throughput per user. So I think these are the techniques that will be helpful to increase the uplink.
Yeah. Okay. When talking about the uplink and applying all these new techniques, this brings also the burden to the handset, right? Because it has to cope with these new techniques. And when we see, as you mentioned, that these sophisticated use cases might transform what we see today as the handset, the normal smartphone, into completely different forms like textiles or whatever. Don't you see there also a big effort in making these new form devices compatible and coping with all the needs to require and to meet the requirements of the performance that the end users are expecting? Because it's a big transformation, right? Also on the handset side.
So, right. But I think while we have many such devices, they may not all directly communicate with the wide area network. We may still have a device which may not, like a box like this, but may not even have a display, because it's just there to make the connectivity to the wide area network, and you keep it somewhere near you. But it's all these other devices just talk to that sort of gateway device. So device is essentially becoming a network in itself, not just on the body. It could also be in other scenarios, like in the verticals, especially. If you think about this time-sensitive networking in 5G, we are already designing for the device to serve multiple robots, things like that. So we have to think of the device as a network, I think, in the 6G timeframe. That's something I didn't mention in my presentation, but that's one of the key transformations that we are thinking about, what we call the sub-networks. What is a device today essentially becomes a sub-network with the ability to move between sub-networks and visibility of all the devices behind that wide area device available in the network. So these are some of the changes we have to work on.
Okay, good. Maybe another point, curiosity that I have is with 5G, we are seeing an attraction of the mobile network being used to support critical services. This was never the purpose of the typical mobile networks in the past when looking into 2G, 3G, and 4G. So it's now, because of the characteristics of the 5G, becoming an option. Do you see this is the way also into 6G? So we will start to see critical services like emergency services or any other connectivity that needs to be fully reliable to be one of the pillars of the 6G use cases?
Absolutely. As I said, I believe in the fact that the next generation will optimize and make the new use case of the current generation more efficient, right? So 5G is the first time we are introducing this industrial IoT characteristics, as you said, and we probably don't get it right the first time. So I think there'll be a major focus on optimizing for verticals in 6G. We will learn from some early deployments, and then we will introduce the learnings into the 6G system and really make it lower cost so that it gets much more widely adopted. I mean, this is the trend I pointed out in the beginning. We tried to introduce data in 3G, but really took off in 4G, right? And in 4G, we introduced IoT, really didn't take off until like recently. And 5G is still using 4G IoT, basically. And likewise, we introduced IIoT in 5G. It really doesn't take off until 6G. 6G is when we learn from the experience, optimize it further. And there are other aspects to it, like the network itself has to become more flexible and agile, because the way we deploy for verticals is quite different from the way we deploy for wide area networks. We need much smaller scale networks, more flexible deployment types. We don't want to deploy on custom hardware for verticals. We want to deploy them in generic computing. It could be on-premise cloud, or it could be in edge cloud. So I think these are the things that we will have to do differently to make it really optimized for verticals.
Okay. Maybe a last one from my side in the interest of time. How do you see 6G making the life easier or more difficult to the growing Open RAN environment? So we are starting to see this growing more and more compared to or not compared, but in par with the traditional network suppliers. Do you see that Open RAN will evolve into the 6G, and we will have this two architectures more closed, and on the other side, the Open RAN open? How do you see this evolving into the future of 6G?
Yes, that's a really good question. I think that we will probably see a more openness in the higher layers. So today, we have split the 5G into a DU and a CU, and then we have the core. For those of you who are not familiar, DU is the distributed unit that captures all the lower layer processing, layer 1 and layer 2 real time, and then CU is the more central unit that does the higher layer IP level processing, and then we have the core network. I think we'll see a lot more openness in these higher layers and the core, whereas the more signal processing intensive parts and the radio will be together and probably not open. That's my feeling. Although O-RAN is trying to make the radio and the distributed unit more open, but to me, it seems like that's a place that's hard to be optimized and open at the same time, because they are too coupled. I would say, like the decisions that we make in the real-time processing very much depend on how the radio is built, what is in the radio, what's not in the radio, all that. But once you're past that, I think it's much more friendly to implement on, say, microservices-based architecture. And so it makes sense to become more open. And that's also the place where I think you have the biggest bang for the buck from making it open. Because services, when you think about why you want open, you want it for new services, easy to introduce new services, have more vendors, have more scalability. I think all of this will be achieved. And it only matters for these higher layers. The lower layers, it's cell-specific processing. And it doesn't really make sense to say, okay, we want to make that very open. At least that's my feeling. Yes, so we'll have O-RAN in the sense of, all of the higher layer processing is going to become much more microservices or services based and more open. And I think the lower layers will stay the same. I think more or less in terms of openness.
Okay.
That's highly speculative. It really depends on how the industry evolves over time. Yeah.
Of course. Yeah, but highly appreciated. Thank you very much.
Yeah.
João, maybe over to you. I could continue with many questions, but you have the time. You are the timekeeper, so
we still have about 10 minutes for further questions. I would like to ask my guests, the other guests, if they want to ask some question. Perhaps I will ask Ana Aguiar. She introduced me to both of the guests. If Ana wants to say something or to ask some question, not to me, please.
No, thank you. Thank you very much. Yes, I do have some questions. First of all, thank you, Harish, for accepting so openly the invitation to present your work, and thank you, Pedro, for your availability. It was a very nice, very interesting discussion. I do have one question, maybe first picking up on one of the last things that Pedro asked, and I warned him I was going to ask him about this, this overrun question, which is, what do you operators, what will you demand from equipment manufacturers, suppliers, to adopt other manufacturers?
Okay, it's an interesting one. So I would, if I could summarize my answer in one word, would be security. Okay. So the big thing that we are debating on the topic is, as you distribute more and more and have more and more stakeholders and suppliers in the middle of the equation, the bigger the security risk. In theory, of course, but we need to be very sure that we do security by design, and this is one of the key requests that we will always put to a supplier to have network grade equipment in our network. Okay, so this is clearly the main topic. Besides that one, of course, there are very day-to-day operational things that need to meet our own processes, and this is an equipment that has to be capable of being orchestrated with the typical tools that we do with the normal vendors equipment, but I would say the main topic here is security. Yeah.
Yeah, and one question, and this was going to be to both, is well, yeah, it builds also on that. So if we start having many vendors and many open interfaces, isn't this going to increase the management complexity of the network? Also, the less integration, the less you integrate, this also goes for NFV, and the less you integrate, the more complex the management of the network, isn't that so? So is this
absolutely from the operator perspective, this is a key topic, of course, because when we go for an equipment that is from Nokia, Ericsson, whoever, this integration is already granted, right? Because there is a set of tools. So this is a very simple environment, let's say, and controlled environment. So the effort from the operator side is very low. When we have this scattered environment, this creates a bigger burden for the operator, or an opportunity for integrators to come in and do that work for us, right? So this is also an opportunity for new players to orchestrate all this environment for the operator. But it's clearly something that we need to understand how will evolve to avoid jeopardizing all our processes and time to market and so on. Yeah, because
what I would say is automation is a key to make that successful. You know, if you think about the web scalers like Google, Microsoft, you know, how they use the cloud, for example, you know, they're able to install and operate software from anyone on their infrastructure, the cloud infrastructure. And the only reason they're able to do that is high degree of automation. And that's, I think, what we have to achieve in mobile networks. And I would say that they are seriously interested in also the mobile space now. So they want to run all of our mobile network functions on their cloud, and they will bring their full force of automation to mobile networks. And that's, I think, a way this thing will evolve and make it feasible for multiple vendors to create a network together. I think that's what's likely to happen.
Yeah, that's true. I see that. That's, but and then that's I mean, if I'm not, and I take another question that I had. It's what we are talking about here is this less integration in the equipments, also with all virtualization, also of the NFVs, all these network services becoming virtualized, services that are today very, very high. They are integrated, they are very efficient, also energy efficient. And when we move all of this into virtualized infrastructure, I mean, that adds both latency in runtime, but it also adds, doesn't it? And I'm not sure about this, and this is what I wanted to ask you about. What is the, or what do you do you expect any energy consumption cost to arise now, not from the MIMO antennas, but from this generalization of the hardware and this, and microservice, all this orchestration and microservice instantiation of network functions? Will this cost also energy?
Yeah, I would say that this is why I feel like the lower layer processing will not be implemented on general purpose hardware at all. And if you think about it, the newer generations will always be much more complex and designed with the most compute we can manage to, implement in reasonable cost. Whereas if you look at the higher layer processing, they tend to be really just software. And even today, the way it's implemented in the base station, it's already somewhat virtualized, right? Because that makes the development processes easier, even though it's on CPUs, basically, is what I'm trying to say. And this, on CPUs, we will make it closer and closer to the way the cloud implements software. So I think that part, I won't say that there will be a big difference in energy consumption. The real difference comes about in the lower layers. And and for the same reason as you're thinking, I also think that it's very unlikely that we will see them implemented on generic hardware. I mean, what is possible is, highly specialized hardware is also becoming part of the cloud that runs these lower layers. So, you may have network interface cards designed for the RAN and become part of the cloud infrastructure. So that's how it could become cloudified, but not on CPU. I think that's very unlikely.
I agree, and let me add something on top of that. As we've been virtualizing our network functions from the core side, let's say over the last years of our 4G and 5G network, we have seen some lower power consumption compared to the equivalent dedicated hardware. Okay, what we see as our bigger challenge is clearly on the lower layers, so meaning the radio. So either the massive MIMO or the amplifiers, or even more complex baseband units that have to do lots of processing in real time. But on the other hand, we are lowering a bit the power consumption from the pure core functions that have been swapped from dedicated hardware to virtual functions, right? Okay, so this is a good news coming from there.
I think the elastic scaling really helps there. So you can scale the power consumption according to the traffic, right? I think this is one of the key aspects that we will benefit from when you go to the cloud.
Yeah, you have a bigger trunk effect, let's say. You do not need So dedicated resources, right? So you can leverage from shared capacity, and at the end of the day, this will bring the consumption down. And this is something that we are already measuring from reality today. So which I believe is a good answer to your question, Anna.
Yes, that is interesting. So
Well,
does
we
anyone
are
want to ask questions? Maybe.
we are on time to finish. I think it was very, very interesting and make us think about the services that the new generation of 6G will enable us, and to think about. I was thinking about other possibilities like medical services also. I think it could be a very interesting area to explore. It's already possible, but I think it could be much better served by new facilities. But mostly I would like to thank Arish for his availability to share with us his ideas and to share with us his knowledge. So thank you very much. I would like to thank Pedro also for being with us and challenging with questions our main guest, and also Anna for not only for the question but for the introduction. All the colleagues and whoever is watching this seminar, thank you for being here. Hope you have enjoyed it, and also our colleagues from the technical staff at FEOP that have been able to make this possible. Thank you very much. So if you have any question that has not been answered, please contact me and I will forward the question to our guests. So thank you very much once again for being here, and hope you enjoy and have a good time, and join us for the next webinar next month on a different topic. Thank you all.
Thank you very much.
Be safe and well.
Stay safe.
Thank you.
Bye-bye.
Bye-bye.